Hi, Assalamualaikum and a very good morning. So now we are in chapter 2, atomic structure. And now we're going to focus on the subtopic of 2.1 Bohr's atomic model, part 2 of the video. So in this video, we're going to focus on the learning outcome of T, which is the description for the formation of line spectrum of the hydrogen atom. And this is going to be covered in this video, which is part 2 of the video. For the learning outcome of A, B, C, E, and F, we have covered that in the previous video, which is in part 1 of the video. So if you haven't watched that one, please watch it now. For now, we're going to focus on part 2 of the video first. So without any further ado, let us start. So, emission spectra. So emission spectra can basically be divided into two, which is continuous spectra as well as the line spectra. And the continuous spectrum here can be seen as a continuous colors here, in which it has a continuous wavelength without any break. Meanwhile, for the line spectra, we're going to focus on the hydrogen atoms here, in which it only has a certain line which represent a certain wavelength. So, without any further ado, let us look into continuous spectra first. So, continuous spectrum. So, continuous spectrum is basically a spectrum that consists of all wavelength components in which it has an unbroken sequence of frequencies, and it appears on the visible portion of the electromagnetic region. Okay, and this is the visible region, in which means that it can be seen with our naked eye, and it is produced by the rainbow, incandescent solid, liquid, as well as the compressed gases. So when it says that it doesn't have unbroken sequence, it means that it is just continuous without any breaking. Okay, and in experiment, you can look into the formation of the continuous spectrum when you turn on the white light of the incandescent lamp, which is like a normal bulb that you use in your household. And then when you turn it on, you're going to pass through the light into a slit, like a small gap here. And this small slit will produce a very fine line of light, and this is going to be passes through a prism. So the light here going to be diffracted in the prism, and this is going to produce a continuous spectrum that can be seen on the screen. So you can say that the white light spread out into the rainbow of colors, which produces a continuous spectrum. And this continuous spectrum consists of all wavelength, and each color merges into the next without any break. Now, we're going to look into the line spectrum. So the line spectrum is the spectrum that we need to focus more, because it relates to our Bohr's atomic model, in which it usually occurs for the hydrogen atom or for the one electron system. As what you can see here, this is the continuous spectrum. Okay. Meanwhile, below here is the line spectrum. So it only consists of certain line. So the line spectrum here consists of this continuous and discrete line produced by the excited atoms and ion as the electron fall back from a higher energy level, for example n equal to 7, and fall down to n is equal to 2. So we are talking about emission. Okay, and the radiation, which is the photon that is being released, will gonna have a specific wavelength or frequency, and it means that each line here represent to a specific wavelength. For example, the red color here will have a wavelength of 656 nanometer, or will have a specific frequency in which you can relate the frequency. For example, lambda is equal to c over v here. Okay, and of course you can find their frequency by bringing the lambda below here. So it is interchangeable. Now, for the formation of line spectrum, you can see that using a diagram here. So it started with a discharge tube which consists of hydrogen atom. So using a high voltage, the emitted light of photon is separated in the prism, where initially the light of the hydrogen will pass through a slit, And when it passes through a prism, this is going to be separated according to its wavelength, and this image is translated on the photographic plate. And this is going to only produce a certain line here. For example, a red color line, a green color line, the blue as well as the purple color line here. And these images here is known as the spectral line, or known as the line spectrum of the hydrogen atom. Okay, and now we're going to look back into the postulates that we have learned in the previous video. So, as mentioned, we're going to focus more on the emission part. So the emission part happens when there is a transition from a high energy level to a low energy level involving electron of a hydrogen. So, as what you can see here, the photon can be produced when the electron goes from n equal to 3 to n equal to 2, and this is going to produce a photon here. At the same time, you can also get another photon when the electron fall from n equal to 4 to n equal to 2. And this is going to produce a green color photon here. And you're going to repeat the same process. For example, n equal to 5 drops to n equal to 2. And this is going to produce a blue photon here. And then you're going to repeat it again, n equal to 6 to n equal to 2. And this is going to produce a different color of line, which is purple here. Okay. And you have also learned about the energy level diagram, in which the energy level diagram will depends on the gap in between one energy level to another. For example, in this case, the energy gap between the first orbit to the nucleus is very, very huge. So it's going to be very huge here. And then here to here, it gets smaller and smaller and smaller. So the similar thing happens in your energy level diagram. So basically, we're only going to focus on this part here. So you can always draw this again in terms of the energy level diagram. So you can say that 3 into 2, one transition, 4 into 2, another transition, 5 into 2, another transition, and 6 into 2, another transition. Okay, so energy level diagram, you are okay with that. The Bohr's atomic model, you are okay with that. But now we're going to see on how a line spectrum can be produced here. So for a line spectrum, we're going to focus more on the colored photon here. So the photon can only happen when there is a transition. Mesti ada perubahan energy level. Elektron dari yang tinggi kepada yang rendah. So we are talking about the transition. So for the red color here, we can say that it goes from n equal to 3 to n equal to 2. So this is going to produce a red line here. Next, for a green color line here, it goes from n equal to 4 to n equal to 2. For the blue one, it goes from n equal to 5 to n equal to 2. So you're going to create another line. And then lastly, you have n equal to 6 to n equal to 2. And then you're going to create another line here. So similarly as before, when the gap gets closer, you mean that the line gets closer and closer to each other. It means that it refers to a higher energy region. So the energy is increasing from the left hand side to the right hand side. Okay, so the similar goes to here. When it becomes closer and closer, it means that the energy got higher and higher. So when energy increases, you can always relate back to the wavelength. So for example, energy is equal to hc over lambda. So when energy increases, the lambda going to be decreases. So you can say that the lambda going to decreases. And as mentioned here, I always talk about going into n equal to 2, n equal to 2, n equal to 2, and n equal to 2. What is so special about the ground state of n equal to 2? So basically, the ground state of n equal to 2 here refers to a Balmer series. So what does this really mean? So the idea of Balmer can be seen more clearly using the energy level diagram as shown here. So the Balmer series here, as what you can see, is the name when the electron drops from a higher energy level into n equal to 2, which is the ground state. So it doesn't matter how high the electron is, as long as it drops to n equal to 2, then it is known as the Balmer series. Okay, so Balmer series, N1 here refers to the ground state, and N2 here refers to the excited state. Okay, and for the ground state here, it needs to drop at n equal to 2. And for n, for the excited state, it doesn't matter where the line is coming from. As long as it drops to n equal to 2, then it is a Balmer series. And I say that the Balmer series is very, very special because it drops in the spectrum region or the radiation region in the visible part of the electromagnetic radiation. So the Balmer series will drop in between this visible region. It means that we can see the line with our naked eye. Okay, and this is why most of the question will come in the Balmer series. However, question can also come in different series and in which you also need to know this. Okay, for example, let's say if you have n equal to 7 and then it drops to n equal to 1. So what series is this belongs to? So you only look at here, when n is equal to 1, where it drops into 1, it is known as the Lyman series. And for the Lyman series, it drops at the ultraviolet region, which is in here. So the ultraviolet region, we cannot see it with our naked eye. Okay. Meanwhile, for Paschen, it happens when a high energy electron drops to n equal to 3. Okay. And this belongs to a spectrum region of infrared. For Brackett, it happens when the ground state is equal to 4, and this can happen when 5 drop to 4 or 6 drop to 4 or any other transition higher than 4 drops to 4. Okay, for example, 5 to 4, 6 to 4, 7 to 4. So this again will refers to infrared. Meanwhile, for Pfund series happens when the high energy electron in the excited state drop from 6 to 5. Okay, and this region here is known as the infrared region. Okay, and you can also make a mnemonic for that. For example, Lyman, balik, pasang, bracket, Pfund. And you know that the ground state here refers to 1, 2, 3, 4, and 5. And here, for the excited state, it needs to be greater than the ground state here. So it can be 2, 3, and so on. And for Balmer, 2 here, the excited need to be bigger than 2, which is 3, 5, and so on. And you can also do the rest according to here. And for the radiation region or the spectrum region, we can say that it started with a UV, visible, and the balance tree here refers to IR. To understand more about this, let us look into the question. So for example 1, the following diagram depicts the line spectrum of the hydrogen atom. Okay, and the line A here refers to the first line in the Lyman series. So the Lyman series here is the keyword. So when we are talking about Lyman series, we know that the ground state is equal to n equal to 1. Okay, and for question A, it's stated here which of the following line correspond to the shortest wavelength. So as mentioned before, when the gap gets closer and closer and closer, you know that it's gonna go increasing in energy. So you know that from here to there, it's gonna be increasing in energy, and as a result of increasing in energy, the wavelength gonna be decreases because you know the formula of E is equal to hc over lambda. When energy increases, lambda decreases. It is inversely proportional. So, which of the line is the shortest wavelength? You can say that line E will have the shortest wavelength. Okay. How about the lowest frequency? So the lowest frequency, you can always relate it back to energy where E is equal to H nu, HV, okay, which refers to frequency. So when we have a lower frequency, then we're also going to have a lower energy. So the one with a lower energy is line A here. So we can say that it is line A. For question B, we need to draw the energy level diagram for the corresponding line spectrum. Okay, and in order to draw the energy level diagram, we need to know the transition first. So let us do that in the next slide. So in this line here, you know that it appears on the Lyman series, and the ground state of Lyman series is n is equal to 1. And you know that the energy increases from A to E. And this is our first transition. So you know that this transition happens from n equal to 2 to n equal to 1. Meanwhile, for B, happens from n equal to 3 to n equal to 1, because the Lyman series will have a ground state of n equal to 1. And C, similarly, n equal to 4 to n equal to 1, D, 5 to 1, E, 6 to 1. And when we are talking about energy level diagram, we need to be able to draw like a graph here, which is the y-axis here going to be the energy, and on the x-axis here, we're going to draw the energy level. So started with a huge gap, and then it gets smaller and smaller and smaller and even smaller. And we need to label the energy level diagram. So let's say if I start from 1, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and n equal to 6. And I know that the n equal to 1 is the lowest level, the ground state of the Lyman series. Okay, so let's say dropping from 2, we have line A here. So line A here happens when 2 drops to 1. So we do need to label it as A. For B, it happens when the excited electron from n equal to 3 to n equal to 1. And for C, it happens from 4 into 1. Okay, and for D, it happens from 5 into 1. And for E, it happens from 6, energy level 6 into 1. And you label it as E here. And this is how you are able to convert the line spectrum into the energy level diagram. Now we're going to move on to the next example, which is example 2. For example 2, we need to describe the transition of electrons that leads to the line W and Y respectively. So we are given the line spectrum here, and it gives you the Balmer series here. So you know that the ground state of the Balmer series is n equal to 2. And as mentioned, when the gap gets closer and closer and closer, you know that the energy increases here. And this is going to be your first transition. So the first transition here must be 3 into 2, because we are in Balmer. Okay, so the first transition is from 3 equal to 2. For W, we can say that it's going to be n equal to 4 to n equal to 2. Here 5, 2, 6, 2, and Y is equal to n7 to n2. Okay, so we can say that for W, it occurs when there is a transition of electron from n equal to 4 to n equal to 2. For Y, you can say that it happens when there is a transition of electron from n equal to 7 to n equal to 2. As simple as that. Now we're going to move on to example number 3. So which of the line in the Paschen series correspond to the longest wavelength of photon? Describe the transition that give rise to the line. Okay, so you know that you are given a Paschen series, and you need to remember where is the ground state of the Paschen series. So remember the mnemonic: Lyman, balik, pasang, bracket, Pfund. So if Lyman, the ground state here gonna be 1. If Balmer 2, Pasang, which is Paschen, is 3. So you know that the ground state here is equal to n equal to 3. And then they ask you which of the following line represent the longest wavelength. So as usual, you need to see the gap. So when the gap get closer and closer and closer together, it means that the energy increases from A to E. Means that here is a higher energy. So when here is the higher energy, then it's gonna have the shortest wavelength. So you know that here will have a lower energy, A here. So when it has a lower energy, then the wavelength gonna be the longest. So you know that A gonna has the longest wavelength. And then it asks you to give the transition. So when it asks you to give a transition, you need to mention from into what level. So in this case, you know that it needs to drop to n equal to 3. And because this is the first line, so we can say that it dropped from n equal to 4 to n equal to 3. So the electron moved from n equal to 4 to n equal to 3. Okay, so I think that's all for today's video. See you again some other time. Bye!